Welcome to the second part of the video for the analysis of the data that we obtained from the Pendulum Investigations Lab. So here's our data, and I've just put boxes around them to group them into the sets of 3 repeats for each size of pendulum bob and for each length of pendulum. In this next part, what we're going to do is to calculate the average period for each length for each sphere. And the way we do that is we're going to calculate the average of the measured period and divide by 10 to get the average period of one oscillation. We divide by 10 because these times represent the times for 10 oscillations. Okay, and we just want the times for one oscillation. Okay, so let's see how to do that. Okay, so what I'm going to do first is to calculate the average for the period for 10 oscillations for the 10 gram sphere and a length of pendulum 20 centimeters. Okay, so to do that, we add them together first. So 9.14 plus 9.00. You don't need the trailing zeros, but I just put them in anyway. Plus 9.07. So let's add those together. That's the sum, which is 27.21. We need to divide that answer by 3. And this gives us the average period for 10 oscillations. And then let's divide that by 10. And that gives us 0.907. That's the average period for one oscillation. 0.97. Okay, so now we can continue and do the rest. So for example here, let me just arrange this a little bit better. Okay, so let's do now for 10 gram sphere, but this time for 40 centimeter length. I'm going to speed it up by using a parentheses to add the numbers together. So 12.82 plus 12.8 plus 12.77. And then I'm going to divide that by 3 and divide that answer by 10. I could have divided by 30 here and got the same result, but this is fine. And let's round the answer to 2 decimal places. So this is 1.279, so I'm going to round up to 1.28. Okay, let's do the next one now. So this is 15.57, add 15.65. I'm going to add that to 15.67. So this will give me the sum, and I'm going to divide that by 3. This gives me the average. I'm going to divide that by 10. So that's 1.563. Round that to 2 decimal places, and that's 1.56. And this is 9.15 plus 9.04 plus 9.17. And then let's divide that by 3 and divide that answer by 10. And we get 0.912, so that should go over here. Now we're going to take the average of these 3 numbers 12.88 plus 12.86 plus 12.7 and divide that by 3. And we've got 12.8, and of course we need to divide that answer by 10. And round it to 2 decimal places, that's 1.28. Okay, next one, the last one. So to find the average of the measurements for sphere 2 at a length of 60 centimeters, we've got 15.57 plus 15.575 plus 15.7. Okay, and then we're going to divide that by 3. That's the average, and then divide that by 10. And we've got 1.57. All right, so now we have the average periods for different lengths and different spheres. So let's have a look at analysis. Discuss the influence of the following factors on the period of oscillation of a pendulum: length, weight of bob, or diameter of bob. Which factor has the strongest effect? Which has the weakest? So what we're looking for is what factor causes the biggest change in the period. So if we double the mass, what do we notice about the average period? It doesn't really change that much. So the mass is not having a big effect. Now the diameter of the bob is related to its mass, okay, because the more clay we use, the bigger the ball is going to be. So the weight and the diameter are really speaking about the same thing, and both those things seem to have very little effect on the period. Now if we change the length, we do get measurable increases in the, when I mean measurable, perhaps we should say, larger increases as we change the length. So as we go from 20 to 40, we see we've added on about 0.3 of a second, and as we go from 40 to 60, we've added on another 0.3 of a second. Okay, so you can write a couple of paragraphs just to explain that kind of analysis. Okay, the next thing is using graph paper, plot the graph of average period t against a length of pendulum. Ensure your labor axis indicate the units. Try to fit a function to the points. So let's just do it step by step. We won't try to fit a function at this point, although I can show you how to do that later on. Now, let's plot these on graph paper. So let me insert some graph paper into this. And you can, of course, use a separate piece of graph paper. Okay, so there's my graph paper, and I need to plot the average. So this space here really is too small for us to plot the graph, so we'll have to add another sheet. Yeah, so I apologize about that. So using graph paper, plot a graph of average period against the length of the pendulum. So what we're going to have on the x-axis is the length of the pendulum. Let's choose our lower limit. We've got, we want to go from 0.2 to 0.6. We could choose to actually go from 0. Okay, and then I want my graph to use the paper that I have in front of me. Okay, so I want to make use of this entire space. So let me count how many boxes I have. I'm counting in 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 there, and I need to span from 0.2 to 0.6. So okay, so what this tells me that if 4 boxes represents 0.2, I think we can fit it all in. So that's 4. 1, 2, 3, 4. 1, 2, 3, 4. Now that's going to be too small. So what I'd like to do, perhaps I just made the calculation wrong in my head. So we've got 12 boxes. Okay, each 2, okay, will represent. So perhaps we should do this then. If we call that 0, that's 0.1. And then if we make this 0.2, okay, I think we're getting somewhere now. This is 0.3, 0.4, 0.5, and 0.6. So here we've chosen a scale that maximizes the use of our area we have here. So what I'm going to do, I'm just going to draw an axis line right here. It's always a good idea to show which direction is positive. And then if that's 0, that would be 0.005, and this will be in the middle. That's a 1. My penmanship is not so good. There we go. Okay. All right. Now let's label that axis. That's length, and that's in meters. Okay, very good. Now, our vertical scale needs to go from 0.9 to 1.56. So if we went from, say, 0 to 2, that would be great. So there's our 0, and let's count how many boxes we have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so 16, so we want to break that up. So we could say 8 boxes. It's a little bit of an inconvenient scale, but we can go with it. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, we'll call that 1. And that means that this over here, halfway, is 0.5. And then over here will be 1.5, and over here will be 2. Okay, so here I've tried to make use of the area of the graph, and I'm going to draw it in my axis now. And that axis is time, or period. Oh, it's hard for me to write sideways. Perhaps it would be better to put period in seconds. Okay. Great. Okay, now let's start plotting the values. So at 0.2 meters for sphere 1, I have the answer is 0.97. So that's a 0.2 meters. So here's 0.2. I need to go to 0.97. That's almost 1. So let's have a look at how this works. If that's 0.5, this is 0.75. Okay, so each one of these is worth there will be an eighth, because there's a half there and this is a quarter. So I'm just going to write here, if that is, this will be this is worth 0.25 and this is worth 0.125. Okay, so this gives you an idea how much each square is worth. Each square is worth 0.125. Normally we want to kind of break it down so like that, because it makes it harder to read. but I'm just going to leave that one. I'm going to leave some kind of marker here to help us just plot our points. Okay, so each one of those squares is 0.125. First data point at 0.2 meters. We're just under the 1 second mark. So we should be here. There's 0.2. We're just under there, okay? All right, now let's go to 0.4. Length of 0.4, we're at 1.28. So here's 0.4. This is 1.125, and this would be 1.25. And we don't want to go more than that. We just want to go slightly above there. Okay, because this is 1.25 and we're at 1.28. Okay. All right, so the next one is 1.56. We can pretty much round that off to 1.5, just slightly above 1.5. Here's 0.6, so we're at slightly above 1.5. So yeah, if we read across there, you see there's a 1.5 line, and we're just slightly above that one. We don't go to the next level here, because that over here, see, that would be 1.625, and we don't want to go that high. You can see that these two are pretty much equal to each other in the sense that the times for the sphere 2 are very similar to times for sphere 1, and so if you were to plot them on the same graph, we could use, say, a different color, or you could use a different symbol, okay, but they pretty much on top of each other, okay. And then you can just put a legend. If you don't want to use colors, you can use different shapes, okay, like for instance use an asterisk and for one of them. So here this would be 10 gram bob, and the other one will be for a 20 gram bob. As I said, we won't worry about trying to fit a function through that, so please ignore that at this point. So, okay, let's just check we did the right thing. We labeled our axes and indicate the units. So period in seconds, yes, and length in meters, yes, we did it. And we should give our graph a title. So we could call this the typical title for this. You would explain that's the variation of pendulum period with pendulum length for pendulum bobs of different mass. With scientific writing, don't be scared to repeat words for clarity, even though you know it seems a little bit what could we say, verbose, but it's clearer if you just repeat it sometimes, so don't be afraid to do that. Variation of, so I repeated pendulum quite a few times here. Variation of pendulum period with pendulum length for pendulum for different pendulum bob mass. Yeah, I should put something like that. For pendulum bobs of different mass. How about that? Oh, I spelled different wrong. Okay. All right, so we're looking at this. It looks pretty much like a straight line. If we did it carefully, it would actually look like it had a slight curve to it, but it's pretty interesting. It can't be a straight line because that would indicate if you had a pendulum of 0 length, then the period should be about 0.75 a second. Okay, so it's definitely not a straight line. So it's not a good idea to draw a straight line through it. So if it has 0 length, then actually you should expect to have 0 period. So obviously this must curve down like this, but we're not really sure what the function is right now. Just from these 3 data points, you know, if we wanted to draw a smooth a function through that, we'd need more data points. So let's just leave it at that. I think that's reasonable given the small amount of information that we have. So that part's done. All right, let's look at what's next. So for the next part here, it says Galileo is credited with having noticed that a pendulum swings with a regular time. About 40 years after Galileo's death, around the end of the 17th century, Isaac Newton was able to explain the motion of the pendulum effect in terms of the effects of gravity. Newton's laws of mechanics and gravity may be used to derive the following equation for the period of a pendulum undergoing small angle oscillations. So if t is the period equals 2 times pi times the radius of the Earth times the square root of the length of the pendulum, which is L, divided by g, which is a gravitational constant, multiplied by the mass of the Earth. So we see that the period of the pendulum is related to the radius of the Earth and the mass of the Earth. If we were on the moon, we took the same length period, the same length pendulum to the moon, we would get different periods. Okay, so that's interesting to note. So explain how measuring the period of the pendulum of a given length could be used to weigh the Earth. Here is that if we know the relationship between the two, like so, we could take some of our data. So let's take one of our data points. Let's take this one where a 0.2 meter long pendulum has an average period of 0.97 seconds, and we could substitute that into this equation. So 0.97 seconds is equal to 2 pi times the radius of the Earth times the square root of the length of the pendulum, which is 0.2, divided by g. G is a number here, the universal gravitational constant, and it's given 6.67 times 10 to the minus 11 times the mass of the Earth. So we can actually solve this equation for the mass of the Earth. So in order to solve this equation, the easiest way would be to take the square of both sides. If we square both sides, we get this. I'm going to do it step by step. Now if we square this, the result will be this. 2 times 2 is 4. Pi times pi is pi squared. Re times Re is Re squared. And then if you take the square of the square root, you just get what's inside the square root. Like so. Now we can rearrange this to get mass of the Earth. So the easiest thing is to multiply both sides by the mass of the Earth. and we get this. And now we can divide both sides by 0.97 squared. And if we calculate that out, we can measure the weight of the Earth. So let's keep going with that. Okay, let's substitute some numbers in. Okay, now I'm ready to put my number in for the radius of the Earth, which is, oh, right here, it's 6,380 kilometers. 6,380 kilometers, but 1 kilometer is 1,000. So this is actually in thousands, and we can write thousands like this, times 10 to the 3. We need to square that, by the way. Then we multiply that by 0.2, because that's the length of the pendulum. You see, we have to keep the units consistent. We've got this distance is in meters, this distance is in meters, and then G is 6.67 times 10 to the minus 11. And perhaps at this point we should replace pi by its number. So that's 4 pi, let's just put that as 3.14 squared. I'm just going to clear that up, so that's squared. And now we can actually calculate this out, and we can measure the mass of the Earth. So let's put that into a calculator, which can be quite tricky. So if you have one of those graphical calculators, certainly it might be easier. So that's 4 times 3.142 squared times 6380. And on this type of calculator, you put e, that raises it to the power 3. And we need to square that number. Multiply that by the pendulum length, 0.2, and divide by 6.67 e to the minus 11, and there's our answer. Okay, their answer is 4.81 times 10 to the 24. I've just rounded it to 2 decimal places. 4.81 times 10 to the 24. Kilograms. Pretty interesting. So that's our estimate for the mass of the Earth. So let's actually find out what it is. We could do a quick Google search. Or rather, instead of what it is, let's think what I mean to say by that is what is the accepted value. So the accepted value is 3 times 10 to the 24. So our order of magnitude was pretty good. So in physics, sometimes what we're more interested in is the order of magnitude. So we can say here the accepted value, which is based upon more careful measurements with more sophisticated equipment for the mass of the Earth, is 6 times 10 to the 24 kg. So not bad. You can see the order of magnitude was the same. So this is roughly 5 times 10 to the 24, but the accepted value is 6 times 10 to the 24. But that's not bad for being able to estimate the mass of the Earth just using a piece of clay and a piece of string. So I hope you found this useful.